Hey guys, it's Professor Janacek. I want to go over a convergence test. I want to specifically look at the integral test. Not going to go over why the integral test works. It's really not that difficult to understand, but here I just want to go over how to use it. So let's take a look at a series. Suppose we have the sum as k goes from 1 to infinity of just a general series a sub k. We'll begin by defining a function. We'll let f of k define the terms. Now, I will, here in a bit, write my functions in terms of x's just to make it easier. Before we actually use this test, we have to verify a few things. F must be continuous, positive, and decreasing. If it is not these three things, then we cannot use this test. So verify that first. But once we have that, then we are going to look at the integral of our function. Again, I'll write it in terms of x's here, just because that's more common. And yes, this is why it's called the integral test, because we integrate. If this integral converges, then the series converges. And if the integral diverges, then the series diverges. It's that simple. So let's jump right in and try an example or two. Let's take a look at the sum as k goes from 1 to infinity of k over the quantity k squared plus 1 cubed in the denominator. So I'll start by defining the function f of x. Yeah, I'll go ahead and use x's here, of x over x squared plus 1 in the denominator cubed. Yes, I replaced the x's with k's. Just make sure you understand how to verify that this is indeed continuous. Think about that. And positive. And decreasing. Again, think that through. Make sure you understand it. This one's not so difficult if you just remember a little bit of Calculus 1 and some algebra, but make sure you recognize that. Sometimes it's not quite so easy as just looking at it, but I think this one's pretty straightforward. All right, once you can verify that, then we're going to simply take the integral from 1 to infinity of our function, x over x squared plus 1 cubed dx. Don't forget to write that dx. It's important. Make sure you remember what that means. But how do we evaluate an integral with the limit of integration of infinity? Well, we take the limit. I'm going to introduce the new variable b, let that go to infinity, and then I'm going to integrate from 1 to b of x over x squared plus 1 quantity cubed dx. All right, so how in the world are we going to do this? Well, I think we can use a u substitution. Let's let u equal x squared plus 1, then du is 2x dx. Ooh, I'm liking that. That's looking pretty good. So I'm going to do a couple of things. Still have my limit notation. Please make sure you write that down every time. Still integrating. I'm going to go ahead and take that x in the numerator and shove it off to the side with the dx. And this x squared plus 1 in the denominator, it has an exponent of 3, but if I move it to the numerator, I can make that exponent negative 3. Now, things are looking pretty good. I have u, x squared plus 1. There it is, no problem. I still need du though. Du is not all there. So, all that's missing is a 2. I can fix that. Put a 2 in there. Of course, that means I need to balance it with a 1/2 there. Remember, when you're doing this little fill in the blank stuff, do not mix u's and x's in the integrand. It just doesn't make sense that way. Kind of like bad language in calculus world. All right, but I think we're ready to go. You'll notice what we have here. We're going to consider the integral of u to the -3rd du. Make sure you're integrating, not differentiating. When we integrate u to the -3rd du, we actually add 1 to the exponent, not subtracting 1. So we end up with -1/2 u to the -2. All right, again, integration, not differentiation. So over here, I still have the limit notation here in the front. I haven't done that. That'll be the last thing I do. I have this 1/2 there in the coefficient, but now I have a -1/2, and I'm going to multiply by u to the -2 power, but u is x squared plus 1. That's now to the -2 power, and I'm still going to evaluate this. It's a definite integral. Evaluate it from 1 to b. Let's clean this up just a little bit before we evaluate it. Let's see, we have -1/4, so a -1 in the numerator, 4 in the denominator. Also notice that because I have this -2 in the exponent, I'm going to go ahead and move that to the denominator as well. So I'll make that x squared plus 1 with the +2 in that exponent. And then we'll evaluate this from 1 to b. All right, still taking the limit. Evaluating from 1 to b, I have -1/4 times b squared plus 1 in the denominator squared, minus 1/4 times 1 squared plus 1 squared in the denominator. I think we can go ahead and dive right in and evaluate that limit now. If you wanted to clean things up first, you're welcome to, but let's go ahead and see. The only place I have a b is right here. So as b gets really large, b squared gets even larger. That denominator is getting really large, so 1/, that expression gets really small. So that first bit just goes to 0. Wasn't that nice? I notice I did forget that negative there. All right, so now I've got minus a negative, which is going to make it plus. In the denominator, 1 squared is 1, plus 1 is 2, squared is 4, times another 4 is 16, so I have 1/16. All right, so there we go. My integral converges. That means the series converges. I do want to point out that my integral converges to 1/16. I have no idea what my series converges to, all right? So 1/16 is the integral value. This is not the series value. I don't know what the series value is. I only know the integral value, but there is a connection. One converges, so does the other. All right, not so bad. Let's try another one. Let's take the sum as k goes from 2 to infinity of 1/k times the natural log of k. We'll begin by letting f of x equal 1/x natural log of x. Again, take a moment, make sure you recognize that this is continuous, positive, and decreasing. Might take a little bit of algebra and some calculus 1 knowledge to go through that, but make sure you recognize that. Don't take my word for it. Make sure you can verify that on your own. Okay, so once you've got that in your mind, that this is continuous, positive, and decreasing, and now we're going to consider the integral. I'm going to integrate. Notice my k begins at 2, so my limit of integration, my lower limit of integration will also be 2. I'm going to integrate up to infinity of 1/x natural log of x dx. Again, need to introduce a limit in order to evaluate this. Oh. I'm going to take the limit as b goes to infinity of the integral from 2 to b, now of 1 over x natural log of x dx. Don't forget that dx again. Make sure you understand what that's about. All right, now, you might look at this integral. That integrand's not necessarily what many of you would consider pretty, but it's not so bad. Take a look at this. It's going to actually end up being quite nice. So let me first break it apart. You'll see why I'm going to do this here in a second. Let me write this as 1 over the natural log of x times 1 over x dx. All right. Again, I want to do a u substitution. Let's let u equal the natural log of x. Then what is du? Well, du would be 1 over x dx. Check that out. There it is. 1 over x dx. Right there in the back. Awesome. So what we're really taking the integral of, I'm integrating 1 over u du. Again, notice. U is there in the denominator, and du is just there in the back. Oh, really couldn't get too much easier. It looked really difficult, but it wasn't so bad in the end. All right, so I'm still taking the limit. To integrate this, let's see, if I integrate 1 over u du, oh, well, this might seem a little confusing, but it's not so bad. The integral of 1 over u du is the natural log of u. So, when I integrate this, I get the natural log of u, but u, we said, is the natural log of x. So, it's the natural log of the natural log of x. We're evaluating this from 2 to b. All right, so let's go ahead and evaluate this, and then we'll take that limit. So I've got the natural log of the natural log of b minus the natural log of the natural log of 2. Well, as the only place I have a b is right there. As b gets really large, the natural log gets really large, and the natural log of that would also get really large. Now notice that over here, the natural log of 2 and the natural log of that, that's just a number. I don't know what number it is, but at some point it won't matter because this thing is getting huge. And so that's all that matters. In this case, this whole thing goes to infinity, which means the integral diverges, therefore the series diverges. All right, enjoy.